know what you're thinking. Mr. Rees, you need a haircut, and you're right. Mr. Rees is exactly the way I prefer to be referred to. Today we're doing a bit of a deep dive into simultaneous linear equations. Now these are some of my most favourite things on the planet because they're simple, they're straightforward, and as I sometimes say, it's a bit like flossing your teeth. A little bit fiddly, but by crikey do you feel clean and wonderful afterwards. So let's dive right into this problem. Imagine you've got four friends, and let's just say their names are, I don't know, Abbott and Costello, and in the other car you've got Fred and Ginger. Now, Abbott and Costello, very keen beans, and they get up a little bit earlier and they leave on the road trip before Fred and Ginger, who have a very leisurely breakfast, sit in, and they're very thorough, they pack the car, and when they're ready, they go. Now, this is an olden days problem. So Fred and Ginger drive a little zippy little car and it moves right along for the standards of the day, and it does a whopping great 15 kilometres per hour. Abbott and Costello, well, we're not told how fast their car goes, but what we are told is this. They start in a village 20 kilometres further down the road than Fred and Ginger, and they start earlier. In fact, they start at 9:30 in the morning. We don't know how fast they're going in terms of kilometres per hour. The problem doesn't tell us that. What we are told is that by 3:30 in the afternoon, if they don't stop at all, they will be 40 kilometres down the road, which is to say they've travelled a total of 20 extra kilometres. Fred and Ginger, as we know, set off at 11:30 and they're driving a slightly faster car. So how would we go about graphing this? Well, first of all, I'm going to suggest we draw two axes, an X and a Y. So the X by convention is horizontal and the Y by convention is vertical. And because we're being very thorough, we're going to put arrowheads on it because that's nice and tidy. Now we think about which variable goes on which axis. And by, again, convention, the independent variable goes on the horizontal axis and the dependent variable goes on the vertical axis. Now let's think about that. We've got two things. We've got the time of day and we've got how far down the road on the road trip are the two cars. Now, which one of those things depends on the other one? For example, could I say, depending on how far down the road the car is, the time changes? Well, we could, but that would be like shooting this video in reverse.
Whoa, that was a trip.
What I'm going to suggest would be a more natural way to do that would be to go, as time moves on, we know that the cars are further down the road and we have information about how far they are. So I'm going to say that time is the independent variable and distance down the road is the dependent variable, which is to say that distance down the road depends on what time it is. So distance is the dependent variable because it depends on something else. So let's label our axes. The independent variable is time and we're going to measure that in hours, and the dependent variable is distance and we'll measure that in kilometres. And why don't we go and put some numbers on there? So we know that somebody starts the race at 9:30, that's Abbott and Costello, and we know where they're going to be at 3:30, so why don't we just do intervals of an hour? Now, small problem there, you can start to see that we've got this strange little thing where we have hour distances, but we don't have whole hours. So you'll notice the axis there isn't from 9 until 10 or even 9:30 to 10, 10 to 10:30, it's 9:30 to 10:30, and I've deliberately done that. It's a little bit weird, and I want you to notice that it's a bit weird. It will still work, but it's odd. And on the distance variable, well, we know that Abbott and Costello start the day at 20 kilometres down the road, and at 3:30 they're going to be at 40 kilometres down the road. Now this axis is going to have problems, but for the moment I've just put that data in there and I've put a point in the middle just in case we need it. So 9:30 a.m, Abbott and Costello are going to be 20 kilometres down the road. Well, how do we work that out? We find out where 20 kilometres is, we draw a line up from 9:30 or the other way if you like, and that's where they're going to be. And we know that they're going to be 40 kilometres down the road at the end of the day. Same process, and there's our second dot. We can draw a straight line between these 2 points because we're told there's a direct relationship between the time of day and how far down the road they've gone. Well, what do we know about Fred and Ginger? Well, we know at 11:30 a.m. they start. Wait a second, we've got a problem because now we see why our y-axis isn't working for us. The lowest number that we have there is 20 kilometres down the road. Well, that's no good for Fred and Ginger because they start at 0. So I'm going to readjust my axis and now we can start to figure out where Fred and Ginger are. Here we go. At 11:30 a.m, they're at distance equals 0. Now we know that they go 15 kilometres an hour. So at 12:30 p.m., they're going to be 15 kilometers down the road. And now you're starting to see the second problem with my y-axis. I don't have a 5 on there. Now I can rough it in and I can certainly draw a line. But how about this? To draw a more accurate line, if those points were further apart, I'd be able to draw that line with greater confidence. So let's talk about what happens if they go down the road 2 hours. Well, 2 times 15 is going to be 30. Okay, what would that look like? Well, it would look like that. And you can see I can draw a straight line, and this point is going to be very close to Abbott and Costello. Not quite going to catch them. Why don't we just cut to the chase and see what happens at 3 hours? Well, at 3 hours, it's 2:30 p.m. They've gone 3 lots of 15, which is 45 kilometers down the road. And again, because we don't have intervals of 5, I still have to make an approximation on my graph. Or I could adjust the axes one more time. I go 4 lots of 15 is 60. There it is. And now I'm very happy because I've got intervals that are exactly the same as my axes. And you'll notice, of course, that all 4 of those points fall on a straight line. So where do the 2 cars meet? Well, if we find the point of intersection of both of those lines and we drop a line down, we'll see the time, and it's exactly 1:00. Well, it's somewhere between 1:30 and 2:30. It's roughly 2 o'clock. It's probably not exactly 2 o'clock. And now you're starting to see that the accuracy of the units that I use on the x-axis probably could have had a bit more thought. Of course, we can solve this problem exactly using algebra. But for now, I want you to understand that what we have is if we graph data from 2 different equations and we use appropriate units, we can find where those 2 lines intersect.